There we go. So yeah, so we're going to look at polymerization. So yeah, basically alkenes is a long polymer chain. We get polyethenes, and we take off that ethene, we take off that E at the beginning of the ethene, we get polythene. That's what polyethene is. We just get rid of that second E, first E then, and just call it polythene, which is basically the plastics that we use over time. So this bit is, there's a little bit of sort of mechanisms of how we make, how we polymerize ethene, but then a lot of it is just sort of overviews of different types of polythenes, and how they're not necessarily great for the environment. So it's a bit more just information-y, bit of mechanisms, but then a lot of just sort of information as well. So yes, so yeah, look at polyalkenes, polymerization, look at the difference between low density polyethene and high density polyethene and ID alkenes. So polyalkenes, basically how alkenes can make a polymer molecule is they can undergo addition reactions. So like when we were talking about those electrophilic addition reactions yesterday, but actually these are a bit different. And when they make these polymer molecules, they go under addition reactions just with themselves. And we call this addition polymerization. And so basically they're reacting with themselves and they form this long polymer molecule. So what we've got here is actually a way that we can show these polymer molecules. So these polymer molecules can be absolutely huge, and they have repeating units in them. So often what we'll show is we'll show the beginning and the terminal ends. So we'll show either end of them, and then we'll put this repeating unit in, because otherwise we could just have like pages long of just repeating the same thing again and again. So the polymer can be represented by showing the repeated unit with square brackets around it, like we've got here. And the N stands for an unspecified number of monomer units. And when we do this, we don't actually show the double bond, even though we know there's a double bond there. So because it's a polymer, it's always a polyalkene, we basically assume knowledge. So this here is exactly the same as this there, and we just assume that everybody knows about that there. So, and we'll look at it in a bit more detail. But basically N, as you know, stands for an unspecified number of monomer units. So actually, rather than having an N there, what you might actually have is that unit and 500, for example, that could be repeated that many times. So what we're going to have a quick look at is how we polymerize ethene. So ethene can undergo addition reactions with itself to form polyethene. So it's basically a free radical chain reaction. So if you think about when we talked about free radicals the other week, it's one of those chain reactions. In this situation, we don't have to use specific free radicals. So we're just going to say Ra as our free radical. So we're just giving it a generalized formula of Ra. That's the only reason why Ra is there. And it's free radical produced by oxygen initiators. So there's our ethene here. And that's our free radical. And they're going to react together to initiate this process. So that free radical that's come along, I'll show this bigger in a minute, it reacts with our ethene molecule. And well, actually, I might as well make it bigger to start off with. And those pi bonds we talked about yesterday are going to come in handy. So our free radicals here is going to react with the ethene. Now, what happens is that pi bond breaks, okay? Pi bond breaks, and then we have those two electrons here. They're going to be separated equally between each carbon. And what happens is one gets attracted to the free radical over here. We get a bonding occurring between our free radical and our carbon, but then one goes to the end of the carbon. So actually now our ethene, which has taken on the free radical, has also become a free radical itself. So the free radical, like I just said, it reacts with the ethene molecule by breaking the pi bond. One electron goes to form a bond between one carbon and the free radical. The second electron moves to the other carbon. The end result is now this whole molecule, which is Ra just standing for free radical, CH2, CH2, and that is a new free radical that we've formed. So now we're going to polymerize ethene. So we've got this free radical here. What comes along is another molecule of ethene. This is going to act exactly the same as when that free radical came along in itself. So it's going to attract itself to the ethene. This part here is our pi bond. Our pi bond is going to break again. Our two electrons are going to be there. One gets attracted to the carbon and the carbon of the free radical, remembering this is now acting as a free radical, and the other one's going to go to the other carbon. We've got a bond then forming between the carbon and the carbon, and then just an electron on its own, the end of that carbon, and now we have a new free radical molecule, and it's even longer. Was that where we were? Yeah, to create a longer free radical. Then this just continues, and it continues and it continues with ethene molecules reacting with either the initial free radical or the lengthened free radical. So here we go, new ethene molecule, same thing's going to happen. Pi bond breaks, bond forms, pi bond breaks, bond forms to the carbon of a carbon, acts as a free radical on the end, and that just keeps going. So this stage is propagation. So this is chain propagation reactions. Final stage is going to be our termination. And basically that polyethene chain will just continue to go until two free radicals react with each other. Because they can attract to each other, they react with each other. And we call this process, chain termination step, because this can occur at any time. Polyethene consists of different chain lengths. So when we make polyethene, we can have like really tiny polyethene chains, really long polyethene chains. It's random when this can occur, so we can get lots of different lengths altogether. So polymerization of ethene is a free radical chain reaction. It involves chain initiation, chain propagation, and chain termination steps. So let's have a look at some types of polyethene. So we get something called LDP and HDP. So depending on the conditions when we are basically polymerizing ethene, that can actually affect the structure and properties of polyethene. We get rid of the E, we just call it polythene. It's the same product. We can get something called low density polythene, LDPE, and this occurs when we make it under high pressure, so about 1,400 atmospheres, and a temperature about 170 degrees. These conditions cause basically a high level of branching. So that means that our polymer chains can't pack tightly together. It's got low density, it's very squidgy, it's very malleable. High density polythene, HDPE, is formed with a catalyst, a pressure of 2 atmospheres, and a temperature of about 70 degrees. In this situation, we have very little branching occurring. So that means that our chains can be packed tightly together, which creates a dense material, which means it's not going to be as flexible. It's going to be a lot stronger. So some examples. So, before we get to that one, all other polyalkenes. So we'll go through the LDP, HDP in a minute. So propene can actually undergo addition polymerization to form polypropene. So obviously we can have polyethene and we can have polypropene. So exactly the same, but this time this is what it would look like, because obviously we've got that extra carbon here, and this is what it would look like there. We can also have chloroethene, and this undergoes addition polymerization to form polychloroethene. It works exactly the same as that polymerization of ethene. It's just that it's slightly different because they're 2 different molecules. So identify the alkene used to make this polymer. So if we have a look at this, again, remember we never draw that carbon-carbon double bond in the polymer part here. So let's have a look here. Because that carbon-carbon double bond has broken, remember, to make that polymer chain, that pi bond has broken. So we've got fluorine and fluorine at the bottom, which is going to mean that it can't be this one because they're on different sides. Can't be this one, so it has to be that one. Here we go. We've got our CH3 group coming off one of our carbons. Can't be the middle one because there's no CH3 group. Can't be bottom one because there's two. The top one, I know it's in a different position, but it makes no difference. We could rotate that round. It could be in that position. That is fine. We've got two chlorines on different sides of the where there would have been a double bond. So it can't be this one because they're on the same side of the double bond. Can't be this one because again, they're on the same side as double bond and is exactly the same as the top one. So it has to be this one because they're on the different sides of that double bond. We've got chlorine and fluorine this time. Can't be the top one because we've got two lots of chlorine, two lots of fluorine. Can't be this one because they're on opposite sides and here they're on the same side. So it has to be this one. Doesn't matter that fluorine and the chlorine are attached to different carbons. That doesn't matter. And then finally, chlorine and chlorine on opposite sides of the double bond. Can't be the top one because there's only one. Can it be the bottom one? Well, they are on opposite sides, but they're not. They're actually on the same side here. Let's look at this one. Yeah, they're diagonal across from each other and it's hydrogen and hydrogen. So it's this one here. So low density polyethylene. Like I said, it's really soft, it's flexible, and it makes soft, flexible, stretchy plastic. And this plastic has a melting point of about 120 degrees. It makes things such as plastic bags, squeezy bottles, general purpose containers, trays, basically anything that needs to be soft and flexible. So things like tubing as well. It has a recycling symbol of 4. We can have high density polyethylene, and like I said earlier, it is a lot tougher, but it is still flexible. This one has a melting point of about 130 degrees, so that melting point is higher, and that will be because there's less branching. So because there's less branching, it has a higher melting point. It's used to make things such as milk bottle and detergent bottles. So we still want them to be flexible. We don't need them to be like a permanent rigid piece of plastic, like, for example, a pen or a stapler, for example. I'm just coming up with random things, but we need them to be a lot more firmer than a plastic bag. We use for rigid items such as folding tables, chairs, pipes, anything like that. High density polyethylene has a recycling symbol of 2. And then we have polypropene. So polypropene, which obviously is different because those two are polyethenes. This one's polypropene. This is a really tough and flexible plastic with a melting point about 160 degrees. So again, we've got a high melting point, and we use it to make ropes, carpets, rugs, and other textiles, med, lab, and kitchen items. And basically what's great about this is because it has a melting point of 160 degrees, it's able to withstand really, really high temperatures to actually clean them in really high temperatures. So things like kitchen items that need to go in a dishwasher, so it can withstand those high temperatures of a dishwasher. And then autoclaves, which is what is used in laboratories and medical settings to clean equipment. And basically they're like really, really hot ovens, and they kill off all the bacteria and get rid of any viruses that are found on those pieces of equipment. Also used to make certain types of bottles, buckets, containers, and other such bottle tops and molded fittings. Has a recycling symbol of 5. So that is the second to last bit on alkenes. So here we go. Waste polymers and alternatives. There is issues with polymers, massive issues, which we're going to look at now. Polymers, well, polyethylenes, polypropenes, really easy to make. They're durable and they're cheap. So they're great. Economically, they're great. We've got a lot of use for them. However, because they are very durable, it means actually they're really hard to get rid of in a sustainable and environmentally friendly way. Most plastics are non-biodegradable, which means they cannot be broken down by microorganisms. We often use that term a lot, non-biodegradable. We often don't really state what that means. Lots of people go, oh, it means it doesn't break down. And it doesn't necessarily mean that it doesn't break down. It means it cannot be broken down by microorganisms. So it's not going to rot. It's not going to get broken down by anything naturally. It's just going to sit there as it is forever. And lots of people don't really understand the differences between a biodegradable plastic and a non-biodegradable plastic. And it's the fact that they can't be broken down by microorganisms. So because of that, they go into landfill and it just increases and increases and increases in amounts because there's nothing there to break them down. It's just sitting there. Doesn't just go into landfill. We also obviously get plastics going into the ocean. Massive issues with that because marine animals could get tangled up in the plastic debris. But also, although most plastics do not biodegrade, they can break down, which is different. Biodegrade, piece of food can biodegrade. Microorganisms break it down back into its micronutrients they use and they eat them, they get dispersed. Plastic can't biodegrade, or these ones can't biodegrade, but they could get broken up into tiny pieces, which obviously isn't the same thing. And they will become more brittle over time and plastic will break and they fragment into these small plastic particles over time. But they're still plastic, and if you got them all together and squished them all back together, you would still have the same amount that you started with. The issue with these is they're microplastics, and microplastics are posing a really bad and huge issue towards marine animals because they're ingesting them. So it goes into small marine organisms such as plankton, and then it enters the food chain, and then they're concerned that these microplastics are actually getting passed down the food chain from things like plankton, then to the fish that eat the plankton, and then potentially to us. One possible solution to this problem is actually reducing the amount of plastic waste we produce, but we could have some sustainable alternatives. So some methods that we can use for reducing plastic waste includes mechanical recycling, and we're going to look at what the differences are in a bit. Chemical recycling, and there's quite a bit of difference between the two. Combustion of plastics to release energy for human use. And then finally, developing biodegradable and photodegradable plastics. The difference between biodegradable and photodegradable: biodegradable is broken down by microorganisms, whereas photodegradable is broken down by sunlight. So recycling, you always hear, make sure you recycle plastics, and you're always told to look for recycling symbols on plastics, and you need to make sure they are plastics that can be recycled, because not all plastics can be recycled. Often it's not that they can't be recycled at all, it's just that the plants that we have that do the recycling can't recycle those types of plastics, often because it's too costly, it's not worthwhile doing those ones. So here we go. We've got mechanical recycling. That involves getting the plastic, shredding it down to really small pieces, washing it, drying it, and then melting the plastics to then make a new product with it. It's really expensive, and actually you need to sort through the different types of plastics. If you had two different types of plastics in there, they're going to have different melting points. You're going to try and melt them in something, it's not going to work. They're going to have different points where then you're going to have to try and separate them if you've melted them together. And then if you put the temperature high enough so they all melted at the same point, then they're going to solidify at different points, and it's just not going to work. So you need to separate them really carefully. It's why you often hear a lot in the news that they go, oh, lots of recycling ends up in landfill, because sometimes the recycling plants can't actually manage and cope with this sorting. And lots of this sorting happens by hand. So they just get rid of it. And again, anything that you recycle has to be clean. Lots of people put lots of things with food waste on it. So then that adds another stage in. It means it has to be cleaned before it can be shredded and before it can be washed if there's too much muck on it. And often in those situations, I'll just chuck it, and they'll often chuck a whole lorry full because they'll just go, oh, this is all contaminated. We don't want it. So depending on plastic type, the melted plastic can be remolded to make a variety of products. And again, that's depending on the plastic type. We can't do this for all plastics, but we can make things such as carrier bags, bottles and containers, police jackets, pipes, carpets. So you see lots of these things now where they'll say, this bag has been made out of so many recycled plastic water bottles. This carry bag has been made out of recycled plastics. And that's where you get them from. Chemical recycling. This is actually where we break down the plastics into their monomer units. It's very, if you think about it, it's almost like when we digest our food and we break down our macronutrients into micronutrients back to their monomers. When we do this, when we break down the plastics to their monomer units, we can use these monomer units as feedstock to produce new polymers or to make other organic chemicals, because obviously they are organic compounds. In this situation, we don't actually need to separate the plastics carefully, as they do for mechanical recycling, because actually we're breaking them down to those monomer units. So that doesn't actually matter as much because we're chemically breaking them down. That's not actually as important because they're all plastics, are all what's working on them can separate them. However, it's really expensive and it actually requires a lot of energy. So then you have that argument and debate of actually, does this level out? Yes, we're recycling it, great. We're not making new plastic, great. But is this really efficient? Are we using more energy to recycle it than it would be to make new plastics? So an example of chemical recycling where we can use it, one example of chemical recycling is something called pyrolysis. And this is where we break down long polymer chains into shorter chains. And we do this in the absence of oxygen. And we use really, really extreme heat and pressure. And what we get from this is an oil, and we can refine it into diesel or jet fuel. Another example we can use is gasification. So we use really similar conditions to pyrolysis, and we break down plastics to make syngas. Syngas is a mixture of carbon monoxide and hydrogen, and we can use it as feedstock in a variety of important chemical processes, for example, making methanol. So combustion, we could burn plastics. Polymers have a lot of energy inside them. We can burn them to release this energy, and we could burn them, release the energy, use it for electricity. That's great, you think, because reduces plastic waste and the use for fossil fuels. But it produces carbon dioxide, which contributes to global warming. So has a massive negative. So again, it's that balancing act. Is this sensible or not? But we have something that could help. So halogen-containing polymers also produce toxic gases when they're burned. So for example, something like polyvinyl chloride produces hydrogen chloride, and that's really corrosive, so that's not great. But what we can do is we can remove some of these toxic waste products when we combust plastics in a plant. So to prevent things like hydrogen chloride being released into the atmosphere when we burn PVC, we use a base such as calcium carbonate or sodium hydroxide, and we add this to the chimney of the incinerator. So these chimney incinerators, these chimneys of the incinerators, we add these bases to them. And basically the bases are just going to neutralize the acidic hydrogen chloride, because hydrogen chloride is acidic. The bases can neutralize them before they're released. So it produces a salt and a water. So it means hydrogen chloride is not released into the atmosphere, which is really great. These equations are quite useful to know. So sodium hydroxide plus hydrogen chloride gives sodium chloride and water. and then calcium oxide and hydrogen chloride goes to calcium chloride and water. Or we can make biodegradable plastics. How we get them is they're not just pure alkenes. We actually modify natural polymers. So things like starch or cellulose from plants, and we take them and we use them to make the polymers. We basically modify them. So for example, you can get a biodegradable polymer called polyglycolic acid, and that's made from the glycolic acid that we find in sugarcane. Biodegradable polymers can be made from 2-methyl-1,3-butadiene isoprene, which is also made by plants. And what's great about these plastics is they can get broken down by microorganisms, but it's not super fast. It's not just going to happen instantly. This process could take a long time. So yeah, it is better than the other plastics, but it's got a downside. Also, we're using plants to make this, plants that could be used as crops. We're chopping them down, so we're sequestering carbon from the atmosphere. We're taking down plants that would actually also give out oxygen. So again, very debatable subject. And then we have photodegradable plastics. Photodegradable plastics are designed to break down when they're exposed to the UV radiation in sunlight for long periods of time. What we can do is we add light sensitive additives to regular polymers. So we just get the normal polymers that we would make and we add light sensitive additives to them. And we do, the additives catalyze the breakdown of the polymer that we're making. So alternatively, polymers can be made to include certain bonds that we can break when they absorb UV radiation. And what this does is it causes the polymer chain to fragment into small pieces. When they're exposed to the light, photodegradable polymers are first broken down into small plastic particles, and then these particles undergo biodegradation by microorganisms. So actually, it's just speeding up that biodegradation process. So a couple of quick questions that we've covered here. So why is it difficult to dispose of plastics in a sustainable and environmentally friendly way? And that's because most plastics are not biodegradable. What are the products of the gasification of plastics? And that obviously is carbon monoxide and hydrogen. What is the disadvantage of burning plastics to produce electricity? It's not that they have very little energy, they have loads. It doesn't require extreme conditions. It's not a slow process, but toxic gases are released into the atmosphere. What can be added to the chimney of an incinerator to prevent polyvinyl chloride, PVC, releasing hydrogen chloride into the atmosphere when it's burnt? We can add a base. Which one of these chemicals could be used to produce biodegradable polymers? And that is isoprene. And finally, photodegradable plastics are plastics that can be broken down by UV radiation. So that is, I think, alkenes. I think what's going to come up now is alcohols. Yep. So what I'm going to get up now is I'm just going to get up the exam questions in a moment. And then we'll go through a couple of exam questions for alkenes. I've forgotten what we were just talking about then. And then we will probably have a little quick start on alcohols because it's only 5:05. So whiteboard, let's get that open as well. Let's open this as well. Everything's decided now to freeze. What has happened? Here we go. Okay. So we did question 1 yesterday. Well, at least it's part A of question 1. So let's get questions up. Okay, we are going to carry on with that then. So I'm going to talk through, we'll go back over the question that we did yesterday. To finish off question 1. Didn't realise it was a 2-part question. Right. So what we were looking at yesterday is just having a go at drawing these out. There we go. So yesterday we had a look at this question. It was propene reacts with concentrated sulfuric acid to form 2 isomers, isomer E and F. And when you were shown the structure of isomer E, and you were asked to name and outline the mechanisms. Oh, I don't know if I'm showing the screen now, actually. Let me just come back to here. Let me screen share. Screen share. There we go. Show isomer E and isomer F. And so, yeah, so we looked at isomer E, which gave us isomer E, and it asked us what the mechanism is to form isomer E. We said that was electrophilic addition, and we drew out the process of electrophilic addition yesterday. This question continues, and it asks us to draw the structure F. So structure F would be the other isomer that could be drawn, that could be made from this. So that is what we're going to have a quick look at now. So part B, we can draw the other isomers. So I'm just going to draw E above it so I can see what E is, because that is important. Otherwise, I'll try and draw the same thing. So CH3, CH, CH3, OH, double bond O, double bond O. Okay, so basically F is the other isomer. So it's just asking us to draw out F. So basically for here is any correct structural formula, including an oxygen, sulfur, oxygen 3 bonded through oxygen correctly. So I'm going to show you that quickly now. So that would look like this. So we'd have our CH3 still, going to our CH2 this time, and going to CH2. This time we're going to have oxygen bond into that. Sulfur is going to be here. Well, obviously it was oxygen before, it's going to be sulfur. Oxygen going to go here, oxygen there, then our OH group at the bottom. So basically it's a sulfur before oxygen's around it. So that would be structure F. So then our final question for this would be explain why more of isomer E than isomer F is formed in this reaction. So if we have a quick look at them, let's zoom out. We've got E, this one's E. We've got E and F here. So first thing that you're going to get a mark for saying straight away is it is, how many marks is that part of the question? Actually, isomer E. 2 marks this part, so yeah, I am right to do that. Undo. So isomer E. Let's move it down here so we can actually see it. So isomer E is formed from a more stable carbocation. So that will be your first mark. So E is formed from a more stable carbocation. Oops. Where's that gone? Right. So isomer E is formed from a more stable carbocation. And basically why that has happened is that our carbocation is more stable than the other carbocation, and that's because of the number of alkyl groups. So if we have a look here, let me zoom out. If we have a look here at our alkyl groups that are attached, we've got more alkyl groups attached to our positive carbon atoms. So actually, if we have a look at our carbocation that we would form, which is here, this one would form 2. But if we attacked it the other way, then we would actually have 1, so it wouldn't be as stable. So because of it, it's not going to be as stable. So isomer E is formed from a more stable carbocation. This carbocation is more stable as it has a greater amount of alkyl groups attached to the positive carbon. And that's pretty much it for that. So what we are going to look at now is the next question. So I'm just going to go over here to give us some space. Let's get the next, let's get question 2 and 3. They're just multiple choice questions. Actually, I should be able to do it on here. So, number 3, which statement is correct about polychloroethene? So, is it that it has an empirical formula CHCl? Does it decolorize bromine water? Is its brittleness reduced by plasticizers? Is its polymer chain contains, oh, I've missed a question actually. We'll do this one first and we'll come back to it. Its polymer chain contains alternate single and double bonds. Well, it's not going to have alternate single and double bonds, so we can get rid of that one. Its empirical formula is not CHCl, so we can get rid of that. Doesn't decolorize bromine water, which means its brittleness is reduced by plasticizers. So it is this one here. So question 2, which statement is not correct about this molecule? So let's have a quick draw of this molecule. Just quite nice to just double check and practice our drawing. So we've got carbon, carbon, hydrogen, hydrogen, which is our CH2C. Got CH3 coming off here. CH. Okay. So what is not correct about CH2, CCH3, CH2Br? Well, if we were going to name this, we've got propene, it's bromopropene. So yeah, so let's have a quick look. Which is not correct about this? Well, it reacts with electrophiles. It is going to react with electrophiles. We've already found that out. So it's not going to be this one. It forms an addition polymer. It's definitely going to do that. Does it decolorize bromine water? Yep, it's got bromine in it. It's going to do that. So we're going to get rid of that. Does it display EZ isomerism? It does not display EZ isomerism. That is not going to happen. And remember, EZ isomerism is where, for example, if we have this, and then that would be 1, well, that would be our E, and then our Z would be C, oops, C, VR, H. And that can't do that. It's where basically you've got your higher groups next to each other. So we can't do that. So let's clear that. So it can't do EZ isomerism, so it's not that. So it is that one because it can't do that one. I hate those ones when you have to try and explain it that way. So let's have a look at number 4. 2-methylbutene, but2-ene reacts with concentrated sulfuric acid to form 2 different products. We want to outline a mechanism for this reaction to show the formation of a major product. Basically, we need to draw this out. So what we're going to do is we're going to start by actually just drawing out 2-methylbut2-ene, and I can't see the rest of it, but2-ene. So but2-ene, let's draw that part out first. So we're going to have 4 carbons. 1, 2, 3, 4. It's 2-methylbut2-ene, so our double carbon bond is going to be at the second carbon. We've also got a methyl group coming off here, so we've got CH3. I'm just going to draw it as H3C, so I don't have to draw out every hydrogen, which you are allowed to do. I'm going to do that with CH3 here. Okay. It can react with concentrated sulfuric acid, and it is able to form 2 different products. So let's have a look what happens here. So first of all, we need to draw out our concentrated sulfuric acid. So we've got HO, SO3H. So again, you need to know the formula for sulfuric acid. What is going to happen? Well, what is going to happen is, I'm going to do this in a different color pen so we can see it nicely. That pi bond is going to break. The electron from the pi bond is going to come and be attracted to our hydrogen here. The bond between the hydrogen and the oxygen is going to break, and that electron is going to go to the oxygen. I'm going to probably run out of space very quickly. Then we go to the next stage. What happens here is we'll draw out what we've just made. So we've got H3C still, C plus, because now we've got our carbocation, CH3, carbon, hydrogen, hydrogen, CH3. Now remember, this hydrogen here has come from our concentrated, sulfuric acid. This is now a carbocation. What's going to happen is it's going to react now with what is left from sulfuric acid, which is going to be acting as a free radical. So what we will have here is the oxygen that was from the dilute sulfuric acid is going to be acting as a free radical. That's going to have a negative charge. So we'll still have SO3H attached to the side. And because of that, that is going to be attracted to the carbon here, because that's carbocation. It's got a slightly positive charge, and that negative charge is going to be attracted. And to do with electron densities as well, so that is going to be attracted there. So then our final stage, and this is when I discovered I ran out of page, is this. We will have H3C, so this is our product, C, CH3, O, SO3H, C, H, H, CH3. So that is our mechanism for this reaction. You don't need to name it. Obviously, that's going to be our addition reaction that's going on. But basically your first mark, your second mark, and your fourth mark are for the curly arrows. So I'm going to show you where the marks are coming in. So mark 1 is for this curly arrow. Mark 2 is for this curly arrow. Mark 4 is for this curly arrow. And mark 3 is for the structure of a carbocation intermediary. So that is your mark there. That is all that is asking for you to do. So 2-methyl butane, butyene reacts with concentrated sulfuric acid. So you're going to need to know what the process is and then draw your process out, making sure you're including those curly arrows. Oops. Then you're asked to draw the minor product of the reaction. You can draw this as the display formula of it, you can draw it as the structural formula as it, or you can draw it as the skeletal formula for it. Major and minor, remembering, is depending on which where that oxygen is going to bond. So I'm just going to draw it out for you now to show you what that would be. So that would be, that would help, CH3. So that is our minor product. So part C basically asks us, well, why do we have a major and minor? So explain why two products are formed in different amounts. So basically, our major product, which is the one that we drew at the beginning, is formed, and it's formed by a tertiary carbocation intermediary. So our major product is formed by a tertiary carbocation intermediate. That's how I spell it, intermediate. Whereas our second product, our minor product, whereas the minor is formed by a secondary carbocation intermediary. And like we said before, tertiary ones are more stable because they've got more alkyl groups, which means they're more likely to be formed, whereas secondary are less stable, so they're less likely to be formed. So that's actually worth 2 marks. So then we actually want to add that part on as well, which I didn't have space for. So this would get you 1 mark. Major product is formed by a tertiary carbocation, whereas the intermediate, whereas the minor is formed by a secondary carbocation. 1 mark. Second mark comes in for us saying our tertiary carbocation is more stable than the secondary carbocation. And that there would give us our second mark for that. So this one here would be our minor. The other one would be our major. Okay, quite a nice question coming up here. Let's clear all those drawings. What is the empirical formula for 4-hydroxy pent-2-ene? So obviously we've got pentene, which means we're going to have C5 involved. Pent-2-ene, sorry, which means we're going to have C5 involved. So we know straight away that it can't be why is this not working? CH2O. So we know it can't be that. So 4-hydroxy pent-2-ene, well, we know it's going to obviously end in an O because it's not an OH group, it's going to end it. So we know it can't be that. So it's going to be B. Six. Let's have a quick look at what this one is. Z-retinol shown in a diagram is a component in vitamin A. Okay, so here we've got Z-retinol, which is in our diagram, and it is a component in vitamin A. And it wants us to say which of the double bonds labelled A, B, C, or D is responsible for the letter Z in the name. So in this situation, it would be C. And that's because obviously it's an EZ isomer. So this is going to be the Z isomer. And so it was all depending on where this one is. Okay, so that is why it gets the Z, because the Z means that they are on the same side. So that is where that is going to affect it. Then let's do one more really quickly. Oh, no, not that one. Yeah, let's have a quick look at this one. So which statement about E1,2-dichloroethene is correct? Obviously, E means it's an E isomer of 1,2-dichloroethene. So A, it has the same point as Z1,2-dichloroethene. B, it forms a polymer with the same repeating unit as Z1,2-dichloroethene. C, it has the same IR spectrum as Z1,2-dichloroethene. Well, it's not going to have the same IR spectrum because it's an isomer, it's different, so it's not going to be that one. It has a molecular ion peak different from that in its mass spectrum. It's not going to be that because it's made up of exactly the same atoms. It's got the same repeating units. So actually it's not going to be this one either because that can affect it depending on where the positions of them are. So actually it is B. It forms a polymer with the same repeating units as Z1,2-dichloroethene. Their repeating units are going to be exactly the same. And then let's do one more. So 9, which statement about ethene is correct? It has no geometric isomers because there is free rotation around the carbon-carbon double bond. Well, we know that's not true because there is no free rotation around that. That's why we get those sigma and pi bonds being formed. And then we have that limited rotation, so we get EZ isomers forming a lot. So we know it's not going to be A. It reacts with hydrogen bromide in a nucleophilic addition reaction. No. The carbon-carbon double bond is twice as strong as the carbon-carbon bond in ethane. Oh, no. It burns in excess oxygen to produce carbon dioxide and water. Yes, that's actually quite an easy one to get. So, end record.